Okay, so today we're gonna go through the problem that was raised on the movie Blackjack 21. A great movie, by the way. So is it didn't give as much explanation, and I'm sure like everyone who watched the movie probably got a little bit confused of how they got to their answer. So the goal today is to show what was the reasoning on it, like a quick explanation, and later we're gonna resolve the proof of it, and also we're gonna kind of like go through like similar process with a small variation of that problem that totally changes things, right? Like it's crazy how details matter so much when you do data analytics, when you do probability and statistics, right? So I think that that would be the biggest take that I want to accomplish in this video. So let me start with the quick reasoning. So pretty much, let's start with this first half here, right? So pretty much the problem that was raised is that there is three different doors. In one door there is like a car, which is the price, and in the other two doors there is like goats, which is like no one wants a goat, right? So that's the first piece of information. The second piece of information that was given in the movie was that the host knows exactly what is on each door, and he always opens the door having a goat after you choose which door you want to have. So let's say, okay, I have three doors. They tell me, okay, there is one car. Which door do you want to choose? I chose door one. Then the host opens either door two or three, whichever has the goat, and then they ask me back if I want to change my choice. In the movie, they say yes because it increased the probability to 33.3% for a total of 66.6%. So we're gonna try to understand why. So the quick way to do this, you have three doors, right? Each of them with a probability of success of 1/3, right? You know that the host opens one of the doors after you chose door one. Okay, so meaning that you know that the probability between these two doors is the sum of them. And because a goat showed up in either of the whatever the host decided to open, the probability transfer to the other one. That way, that's because it's better to change your choice. If you initially chose door one, the probability of success is 1/3. And after the second piece of information happens, that the host opens the door, if you decided to choose to whatever door he didn't open, your probability will be equal to 2/3, which is a little bit counterintuitively. That's why this problem is so famous, because okay, he opens this door, there is only two doors open, two options. We know the car is in one of them. It should be 1/2, right? That's what like a lot of people think, including me, right? That's what like logically you might come to a conclusion to, right? But what is important, and the reason why this is not the case, we're gonna explain later with good formulation of the Bayes theorem. But the reason why the probabilities didn't get updated evenly between the other two options that were still there is because the host is biased about it, right? He has a systematic door opening process, right? So that's, we're gonna go through like heavier example of why that's not the case later on. Okay, so now the second one, right? The main difference between these two pieces of information, right? The first part stays the same. There is one car, there is two goats, three doors, right? In here, however, this is the deviation that I did, in which the 1/2 that we mentioned before actually makes sense. And here it says that the host doesn't know what is behind each door. The horse opens a door at random and a goat shows up, either door 2 or 3 because we already chose door door 1, right? So initially you have the same situation. You have 3 doors, 1/3 probability on each of them because you chose door 1, right? And later the host reveals either door 2 or 3. Let's say that he revealed door 3 and there is a goat here, but because he chose it at random, this probability gets distributed evenly. So in this case it makes sense. There is only 2 options in which there is the car. There is 1/2 probability on each of them. So in this case, it doesn't matter that you either change your choice or stay with your choice, right? So that's the tricky part. And now we're gonna go through like in-depth understanding of why this is true, right? This is not very convincing, right? So let's try to prove that. So let's write this as long way proof. Okay, so let's start with the first one that it was that was showed in the movie, right? So let's say that let A1 be the event at which the car is in door 1, let A2 be the event at which the car is in door 2, and let A3 be the event at which the car is in door 3, and let B be the event at which the host always opens the door with the goat, meaning that the host is biased about it, and he kind of like has that systematic door opening that we talked about earlier. So why do we set these parameters? So why did I did this formulation in terms of events? Is because I want to use the Bayes theorem to see what is the updated probabilities after I know the information too that was provided to us. Remember that the Bayes theorem is very useful for exactly this, for updating probabilities after more information is provided to you. So having this said, I want to know what is my updated probability of A1 to happen if B happened, right? Remember that we went through this in previous videos of where this formula comes from. Okay, so what is the probability of A1 to happen? Well, you have 3 doors. You know that there is 1/3 chance of it to happen. That's the initial probability you had, right? What is the probability that B happens if A1 happens? Remember that the host knows exactly where is every door, so he's pretty biased about it, and he's always gonna choose the door that has the goat. So the probability that the door that he opens having a goat is always gonna be 100% or 1. And the probability of B to happen, the probability that the door shows up and there is a goat, is always going to be 1%, 100%. So this is 1/3, right? Maybe let's go in more in depth with this exercise over here. The probability that A2 happens if B happens, right? We know that the probability of A2 is 1/3, right? So we know that probability of A1, right, is equal to probability of A2 is equal to the probability of A3, right? And we know that the probability of B is always going to be 1 because the host always chooses the door with the goat. So it's always going to be 1 or 100%, right? So if we go through this, right, it's going to be same principle. It's going to be probability of B probability of A2 to happen times probability of B to happen if A2 to happen. Remember that this is not being affected by you directly. I mean, depending of whatever door you choose, the host is gonna open the door who has like a goat, right? So he always is gonna open that door, right? So this is pretty much same, right? 1/3 times 1/1. This is equal to 1/3. And the same is gonna be in here, right? So what this is like telling us is that even though the host opens a door and left you with two options, the probabilities didn't change, right? Your initial choice didn't change, right? There's gonna be a 1/3 probability. However, because he opened, let's say, the third door, the probability here transfers to this one. It didn't transfer evenly because the host was biased about it, right? So this is 2/3 probability. So you always want to change the doors. And this is exactly what, what the reasoning we had in here, right? The initial reasoning. So this is why the probabilities like didn't get updated evenly. Okay, so now let's go through the long way proof for the second example. Right? So in the second example, things changed a little bit, right? Just simply because it happens at random, right? So what this means is that initially the probability of A1 is gonna be still equal to the probability of A2 and the probability to A3, and this is always gonna be 1/3. Now, but because this is happening at random, the probability to B to happen is gonna be dependent on the different options that you have, right? So there is always three choices, right? The first one is that the car is in the door, right? So what is the car is in door one, and the host, well, has, because they're opening at random, has a 100% probability of opening a door with a goat, right? So this would be pretty much saying that this is the probability, of A1 to happen, right? Because that's what we said, the door in door one, times the probability of B to happen if A1 happens. This part, what is this equal to? Well, the probability of A1 to happen is 1/3. The probability of B to happen if A1 happen, well, if the car is in here, it's going to be 1/2 plus 1/2, right? It's going to be, the both goats are going to be here, so it's 100%. Okay, this is plus the second option we have, right? The event at which the car is in door 2. The probability that A2 happen times the probability that B happens if A2 happens. Well, we know that A2 is 1/3, right? And, right, remember that we chose door 1, right, initially, but if the goat is in door 2, the host has to pick between these two choices. Here is the car, here is not the car. So he has 50% chance of choosing the door having a goat. So times 1/2. Times, and the last possible combination is that the event that at which the car is in door 3. Given that we still like chose our initial choice, right, door 1. So that would be the probability that is in door 3 times the probability that B happens if A3 happens. So we know that A3 is 1/3, right? and the probability of B to happen if A3 happens is kind of the same, right? We chose this door so the host cannot open this door, right? We know that the car is in here and he only has these two choices because he's opening them at random. He has as well 50% chance of opening the door with the code. So this is equal to 1/2. If we sum all these guys, you're gonna see that the probability of B is equal to 2/3. Right? Yeah, this is 1/6 plus 1/6, and this is equal to 1/3. 1/3, and this is 1/3 plus 1/3 is 2/3. Right? Okay. So that was like the biggest change that we have. Now let's go and check the updated probabilities of this, right? So now let's do the exact same exercise as before. The probability of A1 to happen if B happens, again, Bayes theorem. Right? This is equal to 2/3. Probability of A1 to happen is 1/3 times probability B to happen, right? We go back to this, right? So if we are like, if event A happens, meaning that there is a car, there is 100% probability that B will happen if A is true. So, right? So this is gonna be 3/6. It's gonna be divided by 3. It's gonna be 1/2. Okay. Now, the probability that A2 happens if B happens is equal to same formula. Right? Probability of B to happen is 2/3. Probability of A2 to happen is 1/3. Probability of B to happen if A2 happens. So we chose this door, right? We know that in this case, the car is in door B, in door 2. So the chances that the host will open the door is only 50% because he only can choose between these two doors. So 1/2, right? So this is equal to 1/6 thirds, 3/12 divided by 3. So this is equal to 1/4. Okay. And the probability, the updated probability of A3 if B happens, same formulation. Right, so probability of A3 to happen is still 1/3 times the probability of B to happen if A3 happens. Remember that we chose door 1, right? And we know that the car is in here. So there is as well 50% chance that he will open the door having a code. And this is equal as well to 1/4. Okay. Now, having this said, because what this is pretty much telling you, pretty much what we kind of prove here, is that because the host opened the other two options at random without knowing what was in there, right? It was like unbiased totally. There was like an evenly spread of the probability between the remaining two options, right? So if we go back to this exercise, let me just clean this up a little bit more, right? So I hope you were able to follow this a little bit. So let me just clean it up on this side. So we know that the probability of A1 if B happen is equal to 1/2. The probability of A2 if B happens is equal to 1/4. the probability of A3 to happen if B happens is equal to 1/4. So you know that the probability of success, if you stay with your first option, is equal to 1/2. And the probability of success, if you switch either after they open one of the doors, right, this will kind of like transfer to it, because you know that the probability of having the card between door 2 and door 3 is equal to success of door 2 or 3. Well, is the sum of the probabilities, right? So what this is telling you is that whatever the host opens next, the remaining two choices are gonna be evenly distributed with 1/2 probability, 50% on each. So in this case, we go back to our initial explanation. We go back to our initial explanation. In this case, it doesn't matter if you change your choice or not. Okay? So I hope this gives you like a good understanding of the Bayes theorem, and especially why information can change everything, right? And I think this is a really cool problem. It's very famous because it's very counterintuitive, but it's really good if you're able to understand this and get it like in your head. You're in a really good spot on understanding the Bayes theorem, and you're probably are gonna do a really good job on catching details when you're doing data analytics in using probability and statistics. So I hope you like this video and have a good night.